Welcome everyone in our lecture Principles of Mechatronics Engineering. Today we are going to start the topic regarding sensors and the transducers. In this lecture we will briefly discuss some definitions only, uh, and in the next lecture we are going to present the hardware components regarding sensors. So what is meant by sensor as a definition? The term sensor is briefly, in a simplified manner, an element which produces a signal relating to a quantity being measured. So this element can be considered a system. The output is a signal, and the input is simply any quantity from the environment. We can have an example for an electrical resistance temperature element. The quantity being measured is the temperature, and the sensor in this case transforms the input of the temperature into a change in the value of the resistance. So this is what meant by sensor. We have an element, and this element produces a signal as an output, and the input can be any quantity or from the environment, for example, as a temperature here. So the next definition is a transducer. The transducer can be often used in place of the term sensor, but a transducer has more global meaning. So a transducer can be defined as elements that, when subject to some physical change, they experience a corresponding related change. So a sensor is simply a transducer, but a transducer has more global uh, definition compared to a sensor. So any element that makes a change due to the effect of an external environmental variable can be called a transducer. But for a great extent, the sensor is used for producing a signal related to the input variable. Regarding sensors and the transducers, we have to define here some definitions. The first definition is range and span. The range of a transducer is simply the limits in which the input can vary, and the span is the maximum value of the input minus the minimum value. So let's have an example. In case of measuring a force, we use a load cell. So the range can be expressed from 0 to 50 kilonewton, and the span in this case is the maximum minus the minimum and is equal to 50 kilonewton. Error is simply the difference between the result of the measurement and the true value of the quantity being measured. So let's express this mathematically. So the error is the measured value minus the true value. Let's have an example for the error definition. If the measurement system gives a temperature of 25 Celsius and the actual temperature is 24, so the error in this case is 25 minus 24 and equal to plus 1. If the actual temperature is 26, so in this case 25 minus 26 and the error will be minus 1. Another example, when the sensor gives a resistance change of 10.2 ohm and the true change is 10.5, so the error in this case is minus 0.3 ohm. Definition 3 is accuracy. Accuracy is the extent to which the value indicated by a measurement system might be wrong. Let's have an example in order to express this sentence. For example, a temperature measuring instrument might be specified as having an accuracy of plus minus 2 Celsius. What does that mean? This plus minus 2 Celsius means that the reading given by the instrument can be expected plus or minus 2 Celsius of the true value. This is what can be used in order to describe the accuracy. Sensitivity. Sensitivity, it is the measure how much such this sensing element is sensitive to the external input variables. So, for example, it is when we are describing a resistance thermometer, so the sensitivity in this case is how much output per unit input. So input is simply temperature with the unit Celsius, and the output is the change in the resistance with the unit ohm. So in this case, sensitivity is the relationship indicating how much output there per unit input, so 0.5 ohm per degree Celsius. Hysteresis error is simply the maximum difference in output for increasing and decreasing values. So let's have an example on this curve. In the shown figure, the output hysteresis is the difference in the output for increasing and decreasing values. This is the increasing and this is the decreasing, and we can see here that by the decreasing path it doesn't follow the same path of the increasing. So the difference between at the maximum here is the hysteresis error. Non-linearity error. The non-linearity error is the maximum difference from the straight line, which is assumed for representing a linear relationship between input and output over a working range. If we have measured the change of the output of the sensor with respect to the input, this is the output and this is the input, and we got such a nonlinear relationship as shown in the three figures. This is a nonlinear relationship. We have different methods in order to express the linear relationship that corresponds to this nonlinearity. For example, here end range values, so simply connect the first value with the end value of this nonlinear curve. So we got this straight line, and the error in this case is the maximum difference between the nonlinear function and this straight line. By the same way here, this is the second method of linearization. By this method, we simply choose the best straight line for all the values. And the maximum difference in between is the non-linearity error. In the last figure, we simply connect the straight line through the zero origin, such that the best fit for this straight line can be met on this intersection point. And the error in this case is the maximum difference between the straight line and the curve here. Repeatability, and reproducibility. The terms repeatability and reproducibility of a transducer is used to describe the ability to give the same output for repeated applications of the same input value. This means how much often I got the same output value for the same input. The error resulting from the same output not being given with repeated application is usually expressed as a percentage of the full range output. So let's describe these words in a mathematical form. So the repeatability is the difference between the maximum and minimum values given over the full range. This ratio here measures or give directly an expression for the repeatability multiplied by 100, of course. Stability of a transducer is the ability to give the same output when used to measure a constant input over a period of time. For example, when we have a step function as an input, so due to the dynamics of the system, we got a change in the output. This output will take some period of time in order to reach a constant value. So the stability is the ability to give the same output when used to measure a constant input. So it will take some time in order to reach the same input in this constant input in this case. This is what is defined by the stability. If we don't reach the same input, so the system in this case can be defined as unstable system. So next definition is the dead band or dead time. The dead time is simply the length of a time from the application of an input until the output begins to respond and change. So it means when I have an input, change in an input, it takes some time for the sensor as a system until an output can be measured. This time in between can be called as a dead time because nothing happens in this time. Let's have an example. For example, in case of measuring flow using a flow meter, the idea of measuring flow is based on a rotor which rotates, and in this rotor we have a bearing friction. So at a certain instance at the beginning we have some flow, but due to friction nothing can be measured and we have no output until the input reaches a certain velocity till this friction doesn't exist no more. So the time in between this in which nothing happened and in which the velocity is zero, in which the rotor is not rotating also as we had flow, this time can be called a dead time or a dead band. Resolution can be simply expressed as the smallest change in the input value to produce an output. So for a sensor giving a digital output, the smallest change is 1 bit, for example. So thus, for a sensor that gives a data word of n bits, the total is 2 power m bits. So the resolution is simply we divide this 1 bit over the total bits, which is 2 power n, and this is simply the resolution of such a sensor. Output impedance, it is from electrical systems. The output impedance of an electrical network is a measure of the opposition of current flow in both static and dynamic. In case of static is a resistance, in case of dynamic it is a reactance which can be represented throughout an inductor or a capacitor. So simply it is how much your circuit or electrical network can oppose the current flow in it. In other words, this is how much impedance can resist your current flow. Now we begin a new topic here regarding static and dynamic characteristics. We consider a sensor as a system, and such a system has both dynamic and static characteristics. So what's meant by static characteristics? Static characteristics are the values when we have a steady state condition. And for the dynamic characteristics, it describes the behavior between the time and the input value change, and it is the behavior between the time that the input value change and the time that the value by a given transducer settles to a steady state. So by dynamics means the transient state. This is the curve which describes the dynamics. This is transient state curve, and steady state means after the system has reached a constant value at the end. So the following terms corresponding to such static and dynamic characteristics. First one is response time. What is a response time? Response time is simply the time elapsed after a step input. It means we got a constant input and we try to see how the system responds to such an input. As shown here, for a step input, it takes this complete time in order to reach a steady state. So the response time is defined as reaching about 95% to reach the steady state value. So from 0 to 95% is called the response time. Time constant. The time constant is directly defined as 63.2% of the response time of the system. So the time constant is directly 63.2 response time of the system from here to 36.2. When the response reaches 36.2% of the steady state output, this is what we call time constant. The next definition is rise time. What is meant by rise time? Rise time in our definition is the time from 10 to 90% of steady state value, 10 to 90% of steady state value. This is called time. Settling time is simply the time taken to settle to 2% of a steady state value. 2% of steady state value. It means completely when this response reaches 98%. So from 98, the corresponding time value at 98% to 0 is called the settling time. So let's have an example here. In this figure, we considered the graph. This graph indicates how an instrument reading changed with time. It is simply a thermometer which is put in a liquid. At time 0, the steady state value is here 55 Celsius, and since 95% of 55 is 52, so in this case at the value of 52.25, which is this value that corresponds to 95% of the response, the time in this case, the response time in this case is 228 seconds. The response time is 228 seconds. So I am now at the end of this lecture. Thank you very much for your attention.